continue with the kinematics of flow, and so far we have discussed about the velocity, acceleration. Today we will discuss about the deformation of fluid. So, when we talk about deformation, we essentially talk of two types of deformation. One is angular, another is linear. Now, no matter whether it is angular or linear, fluids are supposed to be under continuous deformation, and therefore, the absolute value of deformation is the quantity that does not matter much. If you allow more and more time, the fluid will deform more and more. So, it is not the absolute value of the deformation, but the rate of deformation, which in other words is also expressed in the form of rate of strain, that is what is more important than the deformation itself. So, we will start with the angular deformation, and I will try to present a simplistic picture of a two dimensional fluid element. So, you have a two dimensional fluid element like this. The question is that in general the fluid behavior is more accurately represented by a three dimensional picture. So, why a two dimensional fluid element will be good enough to describe the angular deformation? The reason is very simple, that angular motion can be decomposed into angular motion in different planes, that is, for example, rotation. So, rotation with respect to z axis is as good as rotation in the xy plane. So, in this way you could have angular motions in various planes, and the resultant angular motion is just a vector sum of the individual planar angular motions. So, instead of taking a three dimensional fluid element, if you take a two dimensional element, that may be good enough to get a realistic picture. So, let us say that ABCD it has dimensions like this. Now, after a small time interval delta t, it gets arbitrarily deformed and becomes A prime, B prime, C prime, D prime. So, this deformation is well defined by these angles. Delta alpha and delta beta. The issue of angular deformation is essentially to quantify the rate at which these angles are changing. So, how these delta alpha and delta beta are defined? So, if this is x axis, this is y axis, then this is along x and this is along y. So, these are horizontal and vertical lines, and this line is inclined at an angle with the horizontal, this line is inclined at an angle with the vertical. So, there were two line elements which were originally perpendicular. Now, what is the angle between, new angle between the two line elements? That will give you the understanding of the change in angle. So, to quickly work it out, what is delta alpha? We drop a perpendicular here and let us say that this problem this point is E. So, tan of delta alpha so this B dash E, how do you estimate this length? First of all, you have this length, this displacement of A to A prime in the vertical direction is because of which component of velocity? It is because of the y component of velocity. So, this is V into delta t, where V is the velocity along y direction. Can you tell why in the derivation we take delta t very small? The reason is that if we take delta t as very small, only then over that period of time we can consider V to be not changing, otherwise V may change over time also. Okay. So, then displacement you cannot write simply V delta t, then that will be integral of V dt over the period of time, right. So, then what will be this vertical thing? So, if the velocity here is V, here the velocity is V plus that times delta t, and A dash E is delta x plus a little bit change in the delta x. So, delta x plus some change in delta x. So, if we write that, then B dash E is the difference between these two. So, V gets cancelled out. Now, if you take the limit as delta t tends to 0, then delta alpha will also be small. In a small time you cannot really have a very large deformation or large change of angle. So, delta alpha will be small and therefore, tan of delta alpha will tend to delta alpha. So, if you divide that delta alpha with this delta t, it will be simply all other higher order terms will tend to 0 if you take this limit. So, this let us call this as alpha dot, that is the rate of change of this angle. Similarly, it can be shown that beta dot, that is the change of the angle beta, is del u del y. So, this is only little bit of geometry that we need to work out, but now the concept comes. Two important conceptual definitions that we need to go through. One is the rate of deformation. So, when we say rate of deformation, although deformation can be linear or angular, normally we are looking for rate of shear deformation, but I would say that it is always better to describe it as rate of shear deformation, because you also can have rate of linear deformation or volumetric deformation. So, just to specify it properly. So, rate of shear deformation, it is defined as the rate of change of the angle between two line elements imaginary line elements that were originally perpendicular to each other. Now you can always argue that what is the basis, it is like because the change in angle is continuous from one end to the other, it is just for the sake of definition that one takes originally two perpendicular line elements and then see what is the change. So this should be interpreted as a definition and this need not be questioned, because this is like the grammar of the subject and then the subject is developed on the basis of that. So rate of deformation is basically, so original angle is pi by 2, final angle is this one. So this is pi by 2 minus delta alpha minus delta beta. So the change in angle is pi by 2 minus this. So delta alpha plus delta beta. So rate of the change of angle is alpha dot plus beta dot. Okay. And then we also have a definition of angular velocity. So how do we define angular velocity? Again, fluid is not normally rotating like a rigid body. So different line elements of the fluid are rotating by or having angular motion in different ways. So the angular velocity has to be defined by some artificial definition, and that definition is again, it is the average of the angular velocity of two line elements that were originally perpendicular. So average of angular velocity of these two line elements may be, that is alpha dot. Why minus beta dot? Because as per the schematic, alpha dot is in the positive anti-clockwise direction and beta dot is in the negative or clockwise direction. So that is half of okay. So in this way, this is the angular velocity with respect to z axis. So in this way we can actually write the expressions for angular velocity with respect to other axes as well. So omega x, remember that you have a triad that is in the right handed system. This is how you have the connectivity between x, y and z. So omega z, you see in the derivative first comes x and then comes y. So after z in the anti-clockwise direction first comes x and then comes y. So with respect to x axis, first will come as y and then will come as z, and it will be a cross derivative. Okay. So I mean it is like drawing an analogy. Once you know this, you can write the expressions for the others. Y will be first z and then x. So now if you write the angular velocity vector, you can simply work out and see that this is half of the curl of the velocity vector, because the components of the curl of the velocity vector are given by these terms which are there in the bracket. So, this curl of the velocity vector without giving much physical interpretation has been existing as a very important definition in the fluid mechanics world for a very long time, as introduced by mathematicians, and this is known as vorticity. So, physically vorticity means the rotationality in the flow. So, if there is no rotation in the flow, if the angular velocity is 0, then it is called as irrotational flow. So, irrotational flow now, when we have defined the term vorticity, we will also define a closely related term called as circulation. Circulation is defined as this contour integral of this over a closed contour. So, this integral essentially means that you take a closed contour, follow a certain direction, standard traditional direction is anti-clockwise direction, and then you come back to the same point from which you started. That is how you form a closed loop. Along the closed loop you perform this integral. So, then by using the Stokes theorem in vector calculus, you can write this as curl V dot with eta, where eta is a unit vector. So, let me draw a schematic to illustrate this. So, if you have a closed loop like this, you can take a small ds and the unit vector to this, normal vector to this is eta. So, this line integral can be converted into the area integral, where the area is essentially bounded by this line or formed by this line. So, clearly circulation and vorticity are related, because this is nothing but the vorticity vector. So, you can from here qualitatively say that circulation per unit area will be the vorticity, and let us try to calculate it considering some specific example. Which one? It is not a closed surface. Just an integral, yes, right. Sorry, yeah, this is just an integral. So, it is better to write this as S like this over a surface integral. Okay. So, then let us calculate the circulation for a particular type of flow which we call as vortex flow. So, vortex flow is a type of flow where you have V theta. So, what is V theta? So, you have in the polar coordinate system the direction r and the direction theta. So, V theta is the velocity in the tangential direction. So, V theta is a function of r and Vr is equal to 0. This kind of flow is called as vortex flow. So, example 1 we will consider force vortex. V theta is equal to Cr. So, you can see that from here it looks like the very simple basic expression of V equal to omega r. So, it is like a rigid body type of motion that you see in traditional mechanics of rigid body, V equal to omega r and Vr equal to 0. So, this is like a rigid body rotation, rigid body like rotation of fluid. We will consider a second example which is called as free vortex. Okay. So, how do you get a force vortex physically? You take a cylindrical cup, fill it with a fluid, maybe partially fill it with the fluid and rotate it with respect to its axis. So, you can generate the force vortex, and you from your earlier experience you know that the corresponding shape of the free surface of the fluid is like a paraboloid of revolution. That is the force vortex. Free vortex. So, let us assume that you have a sink, say kitchen sink, and you allow the tap water to flow through the opening of the sink. So, you will find that as the water comes close to the center or the axis, it is moving very fast, it is getting drained out very fast. So, that means this V theta literally tends to get as large as tending to infinity as r tends to 0. So, this kind of flow is called as free vortex flow, and typically these are model problems for irrotational flow. So, let us try to calculate, maybe these two examples I have given, I leave one of these as a homework for you to calculate the circulation, and I am doing the other one. So, let us calculate the circulation for example 2. So, let us assume that because it is a cylindrical system, we take this ABCD as the closed contour and try to perform the integral of the contour integral of so this is circulation, sometimes we give this symbol as capital gamma. So, this is what sum of 4 line integrals AB, BC, CD and DA. That is how if you start from A you can come back to A. So, for AB V theta is in this direction, right. So, V theta is C by R dl is in the other direction. So, this will be minus r d theta or delta theta, right. For BC, the velocity v theta is perpendicular to BC, therefore, the dot product is 0. For CD, the line element is in this direction and v theta is also in this direction. So, v theta is C by r plus delta r, where this is delta r into r plus delta r delta theta, and for dA it is 0. Okay. So, what you are left with is sum total of these two, which is 0, which is intuitively expected because it is irrotational flow. The vorticity is a null vector and therefore, the circulation, which is essentially vorticity times the area, that will also be equal to 0. However, there is a tricky aspect to this consideration. Let us say there is some analyst who instead of this area chooses this contour OBA, then what happens? So, if this contour OBA is chosen, then clearly the total circulation over this contour OBA, this is not 0. The reason is the circulation over the integral for v dot dl over this is 0, the integral for v dot dl over this is 0, but over this it is not 0. So, circulation considering the path OAB is not equal to 0. This gives a false impression that the flow has some rotationality, because circulation has to be 0 for irrotational flow. So, there is a technical flaw in calculating this circulation. The technical flaw is that this point O is a point of singularity. What is a point of singularity? You see v theta is equal to c by r. So, as r tends to 0, v theta tends to infinity. So, the rule is that you can consider any contour in the domain except for a contour that contains or includes the point of singularity. That will spoil the entire integration. So, the moral of the story is that to calculate the vorticity or circulation, or to calculate the circulation to be in specific, you can choose any arbitrarily closed contour, provided that the contour does not include the point of singularity. Okay. Now, in practice, the force vortex or free vortex model as standalone models may not be sufficient to describe the practical problem. So, the practical problem is often described as a combination of force vortex and free vortex, which for example is very commonly used for designing the flow structure during a tornado in the atmospheric scale. So, then you basically design that as a combination of force vortex and free vortex. So, there is a small distance from the center of the or from the axis of the tornado, up to which you have as the vortex as force vortex, and from here you have the vortex as free vortex. Why you do not consider free vortex here is because then you will get the singularity, that is at r tends to 0 you will get v theta tends to infinity. So, that is not practically feasible. So, you have a cutoff radius, and within the cutoff radius you have the forced vortex. So, this model is called as Rankine vortex. So, vortex flows are very important for modeling atmospheric flows as well as modeling the rotational flows in combustors in combustion problems. So, to summarize, today we have discussed about the angular behavior of deformation or the angular aspects of deformation in terms of rotation and shear deformation. But we have to remember that the fluid also has linear and volumetric deformation, and these are very important aspects of deformation. We will take this up in the next lecture. Thank you.